So this video is on position vectors and modelling. So let's start with position vectors. This is something that comes up a lot. If we have a coordinate, let's say A, and let's put A here. Let's say A is equal to 5, 3. The position vector of A is the vector that goes from O to the coordinate A. So it's going to be this straight line. Here we're going to put an arrow this because it's going from O to A, and it's going to be O, A. And the vector is going to be in column form because the origin is just 0, 0. It's just going to be 5, 3 in column form. Let's do another example. Let's say that B is here, and B, let's say, is equal to 4, 1. The position vector of B is going to be this, like that, which is going to be OB, which is going to equal 4, 1 again. So a very common exam question for them to ask is to find the vector AB. So it's going from A to B, so it's going to be this here. And the way we do this is just to follow the lines. So we start from A and we go down here in this direction. So AB is going to equal AO, and then we're going to go up like this, so it's going to be plus OB. And because we know OA is equal to 5 over 3, therefore it's going to be minus OA, so we can get OA, remember it's minus AO, OA relationship, plus OB, and then we can just figure it out. So it's going to be minus, so OA is, we figured out before, 5, 3, and then OB is 4, 1, and then this can easily be done by just putting this minus in to do minus 5 minus 3 plus 4, 1, which is equal to minus 1 minus 2. And this is the vector AB. It's a very common exam question, so just remember when they're asking for a position vector, it's just going to be the vector of whatever the coordinate is. So here's another example of this. Again, they're very common for them to give you like two coordinates, and they want you to find the vector that connects the two. So for these questions, I would always draw a diagram so you know which directions you're going in. So draw a diagram like this, where this is Y and this is X, and let's say, so it's 5, 9, so it's going to be somewhere over here, and B is minus 3, 7, it's going to be somewhere over here. So this is O, this is A, this is B. I'm going to draw in the position vectors like this. Remember, it goes in this direction, this goes in this direction, and we know that OA position vector is going to be equal to 5, 9, and OB is going to be equal to, because we know B, minus 3, 7. And we need to find AB, which is this here that connects A and B, and remember it's going in this direction. So we're going to do the thing where we follow the lines from before. So we start from A, so AB is equal to, so we're going to go down like this in this direction, so AO plus, and then we're going to go up like this to OB, and AO is the opposite of OA, so we can just do minus OA, because remember we're going in the opposite directions here. This direction is fine because we're going in the same direction, plus OB, and therefore we can just do minus 5, 9 plus minus 3, 7, which is equal to, put the minus into this vector to do minus 5, minus 9 plus minus 3, 7, and then we just add the vectors. So minus 5 plus minus 3 is going to be minus 8, and then minus 9 plus 7 is going to be minus 2. And that's the final answer. So now let's move on to some specific questions that they could ask. And this is a fairly common one that requires a specific method to do that I would probably memorize, because it's quite unusual. So you have a parallelogram and we have the diagonals that intersect at this point here, which we've called P. And we need to prove that the diagonals bisect each other. So bisect might be a term that you've heard of before, but you might not know the specific definition of it. Bisect means that obviously the two lines intersect, but they divide into two equal parts. So what I mean by that is the line OP and the line BC are the same length, and likewise the line BP and the line PA are the same length. And we need to prove that these two pairs have the same lengths. Okay, so how are we going to do that? Well, first of all, I'm going to do the same thing that I did in the last video about parallelograms, where this is going to be B because it's parallel and equal in size to this side, and the exact same logic for here, this is going to be A because it's parallel and equal size to this side here. Now let's find OC, this vector here. So OC is going to be equal to, so let's go up like this, from O, so it's going to be OB, and we're going in this direction. And then let's go across like this, also going in this direction, to get plus BC. Now we know both of these because we're just going in the same direction of A and B, so therefore it's just going to be A plus B. So OC is equal to A plus B. Okay, now let's consider the smaller segment OP. So OP, because it's in the same direction as OC, it's kind of parallel to it, although it lies on the same line, it's going to be a multiple of A plus B, because it lies on it, it's going to be a smaller multiple because it's a smaller segment of the line. Now, because they bisect each other, it's going to be a half. But because it's a proof, remember for proofs, look back at chapter 7 if you don't know this, we cannot assume the proof. We cannot assume that they bisect each other, so we cannot assume that this is going to be equal to a half. So instead, we're going to use a trick and say that this is lambda of A plus B, where lambda is equal to how far P is across OC. Now, if they bisect each other, then lambda should be a half, as this should lie exactly in the middle of O and C. But again, because it's a proof, we can't assume that. So we're actually now going to prove that lambda is equal to a half. Okay, now let's do the other diagonal. Let's do AB here. And let's find the vector for AB. So AB is equal to, so let's start from A, let's go across like this here, and this is AO, and we're going in this direction, and it's going to be plus, and we're going to go up like this, OB. We know OB, this is just B, we're going in the same direction, but this time we're going in the opposite direction to this vector, so it's going to be minus OA plus OB. So this is going to be equal to minus A, and then it's just going to be plus B. So that's AB, this whole diagonal here, and let's do the exact same thing, and let's consider this smaller segment, AP. So AP is going to equal minus A plus B, and it's the exact same thing again. We know that this, if it does bisect, it should be a half, but we can't prove that. So instead of being a half, we're going to use this kind of Greek U, where this Greek U is equal to how far P is across a B this time. This is what the Greek letter mu is referring to. Again, because it's bisecting, we don't know that lambda and the Greek letter U are the same size. And now we're going to find an expression for OP using this term that we've just got for AP. So we want OP, and we're going to use this AP expression so we can get mu, and we're going to do OP is equal to, so let's go across here this time. So OA, so we're going to go across it. I might do this in a different color actually. So let's do OP is equal to, so let's go across like this to A. We're going in this direction, so it's OA. And that's going to be plus AP, because we're going up like this, plus AP. And this is going to be equal to, we're going in the same direction, so this is fine, so this is going to be A. And we're going in the same direction as AP, so we can just add this. A plus the Greek letter U minus A plus B. Okay, so hopefully you've followed along so far, but the thing you might be asking now is, why have we done all that? Kind of what benefit is that to us? Well, now we actually have two terms that both equal OP, so therefore we can equal them to each other. So we can do lambda of A plus B is equal to A plus this Greek letter U of minus A plus B. And now let's expand the bracket. So we've got lambda A plus lambda B is equal to A minus this Greek letter U of A plus this Greek letter of U for B. And now what we can do is we can form simultaneous equations by using the coefficients of A and the coefficients of B. This might be something that you haven't come across before. But basically what we can do is we can say lambda A plus lambda B is equal to, I'm going to factorize A out of these two to get 1 minus U, or mu, sorry, of A plus mu of B, and we can now create simultaneous equations of these coefficients. We know that these coefficients are going to equal these coefficients because they're both A, and these coefficients are going to equal these coefficients because they're both B. So we've got two sets of simultaneous equations. Lambda is equal to 1 minus mu, and lambda is equal to U. Now this might be a thing that you haven't come across before, and it's just something that you can do. If you have these kind of coefficients that are the same, you just have A and B, the coefficients will equal each other. So what you can do now is just sub this into here to get that lambda is equal to 1 minus lambda, and then we can put this onto the other side to get 2 lambda is equal to 1, and therefore we can get that lambda is equal to a half. And because you know that lambda is equal to mu, mu is the Greek letter for U, mu is equal also to a half. And remember at the start, this proves now that they bisect each other, because we know that P on both the lines lies exactly halfway on both lines. So therefore these are the same length and these are the same length. So therefore, remember, do a statement at the end for a proof. The diagonals bisect each other. Now, I will level with you, this is hard. It definitely is. I would say it's quite hard. The first time I saw it, I didn't quite get it. What I would advise you to do is look in the textbook, rewatch this section of the video, try and understand it as best as possible, try and understand what's going on first, and then try and understand why we do it, because we want these two things here to both equal OP, so therefore we can equal them to each other and find lambda and mu. So here's another, I think, quite realistic exam question that I made. It's got ratios involved, which I don't think is too uncommon for vectors either. Okay, so for part A, hopefully this isn't too bad. We just need to find the vector A, B. So it goes from A to B, so like this. So the way we're just going to do this is start from A. So AB is equal to, I'm going to go down like this, in this direction to get AO plus, and then we're going to go down like this to get to B, like this, so it's going to be plus OB. we're going in the opposite direction to A, so therefore it's going to be minus OA, and then OB is fine because we're going in the same direction, as you can see. And then therefore that's just going to be minus A plus B. So AB is equal to minus A plus B. So for part B, this is reliant on the fact that you know how ratios work, this 2/3 ratio. It's also reliant on the fact that you read the question, because this isn't actually immediately obvious from just looking at the diagram. So the way that the ratios work is it will divide segments by, so this will be 2 and this will be 3, and then you add the two numbers together in the denominators. This will be 2/5 and this will be 3/5. And this is how it will divide the segments into 2/5 and 3/5. And from this we can figure out AC, the vector AC. AC will be equal to 2/5, and it will be minus A plus B, because it is a segment of AB. And therefore from here we can find the position vector of C, because it will be the OC here. So OC is equal to, so it's going to be, we're going to go up like this, it's going to be in this direction, get OA, and then it's going to come back down like this to get to C, so it's plus AC. So therefore this is just going to be OA, which is A, it works in the same direction as this, A plus, and then the AC part here, plus 2/5 minus A plus B. Expand the brackets to get A plus, or minus, sorry, 2/5 A plus 2/5 B, and then you just do the A minus 2/5 A, which is going to be equal to 3/5 A plus 2/5 B, and then that's the answer. Okay, so for part C, as it gives us A and B, we can now figure out the exact value for OC. So OC is equal to 3/5, and then A is 4/5, and then plus 2/5, and then 7, and then minus 1. Look back in the last video if you don't know how to times a vector by coefficients, but it's pretty easy. It's just going to be everything times by whatever's in front. So it's going to be 4 times 3/5, which is 12/5, and 5 times 3/5, which is just 3. There's going to be plus 14/5, and then minus 2/5. And then if you just put that all into a calculator, do the separate bits. So 12/5 plus 14/5 is equal to 26/5, and then 3 minus 2/5 is equal to 13/5. And then you can figure out the magnitude of OC by doing the square root of 26/5 squared plus 13/5 squared, which if you put into a calculator is equal to 13√5/5. And then for part C, so I just wanted to clear a bit of space for the direction. So the vector is going to be somewhere up here, so we're going to draw a triangle like this. So it goes to the right by 26/5, and it goes up by 13/5. So right angle triangle, obviously, and we need to find the angle between I and the vector, so it's going to be this angle here, and therefore we can use SOHCAHTOA quite easily. This is O, this is A, this is H. We know nothing about H, so therefore tan theta is equal to 13/5 over 26/5, which you can just simplify, you don't really need to anyway, to 13/26, which is equal to a half, but if you just plug this into your calculator it would work. So therefore theta is equal to the tan inverse of a half, which is equal to 26.6 degrees, and that's the final answer. So now let's move on to modelling. So modelling is just applying these concepts to real life scenarios. It's just what you've learned from vectors and just put it into kind of a real life scenario. It's pretty much just a normal question. So here's an example like this. So for part A, hopefully this isn't too bad. We need to find the vector OB. B, so it's going in this direction here. Well, we know the downwards part because it's this here, it's 9.24, but remember it's going to be minus 9.24 because it's going down. But what we need to find is the right component, and we can do this by creating the triangle here, and therefore we can just do SOHCAHTOA in order to find this side here, and this will be the horizontal component of the vector. So let's do that. So this is going to be the opposite, this is the hypotenuse, and this is the adjacent. We know nothing about the hypotenuse and we don't need it, so we're going to ignore that. So using SOHCAHTOA, it's going to be tan of theta is equal to O over A. So it's going to be tan of 22.5 is equal to O over 9.24, and therefore O is going to equal tan. It's going to equal 9.24 times tan of 22.5, which, if you put into a calculator, is equal to 3.83 to 2 decimal places. So the overall vector is going to be, it's going to the right, so this is going to be positive, so it's going to be 3.83, and then this is going down, so it's going to be minus 9.24, and that's the final answer. So for part B, we need to find the width of the trough at the highest point. So if you think about it, this will be this line here. This is the highest point, and this will be the width of it. So we need to find the length of this line. So how can we do that? Well, first of all, we can figure out the length of this line here, because we have this, and we have a right angled triangle, so therefore we can use Pythagoras. So we can do the square root of 9.24 squared plus 3.83 squared. And if you put that into a calculator to 2 decimal places, that just gives out 10. So this here is going to be 10. We can also figure out this angle here because it tells us that O and A lie on a horizontal surface, and as we know, this is a vertical surface. We've got a vertical surface and a horizontal surface, so this here is going to be 90 degrees. So this angle here is going to be 90 minus 22.5, which again you put into a calculator is equal to 67.5. It tells us that the angle BOA is equal to the angle of BAO. Remember these kind of symbols here, this kind of like this here, this indicates angle. So therefore we know that this is also going to be 67.5. And then from here, you can figure this out by using sine rule or whatever, but you will actually also realize this is actually a isosceles triangle, so this is actually going to be 10 as well. And because angles in a triangle add up to 180 degrees, we can figure out this angle here, because we can do 180 minus 2 times 67.5, because those are the other two angles. And if you put that into a calculator, you get out 45 degrees. So this is going to be 45 degrees. And now we can use the sine rule in order to find the length of this line here, because we have this, as we talked about in the chapter 9, we have this opposite side and angle, which is really important. So because we're trying to find a side, remember the side is going to go on top, so it's going to be, I'm just going to call this x, it's going to be 10 over sine of 67.5, and this is going to be equal to this opposite angle and side, so it's going to be x over sin 45 times both sides by sin 45 to get 10 sin 45 over sin 67.5, which is equal to x, and if you solve that in a calculator, you should get out that x is equal to 7.65, and that's the width of the trough, and that's the final answer. Another type of modelling they can do is kind of like mechanics, and I don't think this is too bad. I think this is just another type of vector question they can just apply you on. There's just a couple of things you might need to be aware of. First of all, let's say that we have an object that's moving. So if it has a velocity, we're talking about its vector. So it could be something like this, meaning it has a horizontal component and a vertical component. But if we're talking about its speed, we're talking about its magnitude only. It means we're just talking about the size of the vector rather than its horizontal and vertical components. That's the difference between a vector and something like speed, which is known as scalar, but you don't really need to know that, is that one of them has a horizontal and vertical component, but the other one just has its kind of magnitude component. So velocity is a vector and magnitude is the speed of, let's say, an object. For the difference between two different points, the displacement is the vector, so it can have a horizontal and vertical component, and the magnitude of that vector is the distance. That's kind of the overall. So just know these relationships. If it gives you a velocity vector and it wants you to find the speed, it's just asking for the magnitude. If it gives you the displacement vector and it wants you to find the distance, it just wants you to find the magnitude. So here's an example of this, of a displacement and distance question. So for part A, it's always helpful to draw a diagram. So I'm just going to do that quick. So I'm going to do a quick y-axis and a quick x-axis. Okay, so point A is at 8i plus 6j, so it's somewhere up here. It doesn't really matter where. This is point A. And point B is at minus I minus 3j, so it's somewhere down here again. Doesn't matter too much. Let's connect them both to the origin, like that. Might do that a bit more straight. Like that, and then A like that, with that being O. And we need to find the vector. Let's draw the arrows in for the things before I forget, like that. We need to find the vector from B to A. So this is going to be this vector here. This is a horrible diagram, but hopefully it's good enough. Find the vector from B to A, so it's going to be like this. So what we need to do is to find B, A. It specifically says from B to A, so we need to find B, A. So we need to first of all do this in this direction, so it's going to be B, O, and then it's going to be plus O, A. This is fine, this is in the right direction, but this is in the wrong direction, so it's going to be minus OB plus OA. So it's going to end up being minus OB, so it's going to be minus of this, minus, and then minus I minus 3j, and then plus 8i plus 6j. Expand to do I plus 3j plus 8i plus 6j. Please remember to put a bracket around so you do minus the whole thing. And this is equal to 9i plus 9j, and then meters if we need to be more specific, as it's in meters. And that is the final answer. And then for part B, this is really easy. We need to find the distance between A and B. We know the vector between them, so all we just need to do is find the magnitude of the vector, which is going to be equal to the square root of 9 squared plus 9 squared, which if you put it to a calculator is equal to 9 root 2, and then meters. And that's the final answer. So here's a question on position vectors and modelling. So pause the video, have a go, and I'll go through the answers in about 5 seconds. Okay, so for part A, it wants us to find DF, and there's a lot going on in this question, so just take it step by step and kind of do the easy things first. So the first thing you can realise is that this side here is also going to have a vector of B, because it is the same size and is parallel to this side over here, and it's the same for this side up here. This is going to be A because of this side over here. Now we need to find DF, and this is all to do with the ratios that they give us. It tells us that ED divides BC in the ratio of 1 to 3. So what we can tell from this is that this is going to be 1/4, and this is going to be 3/4. Remember how a ratio works, it's whatever's you're focusing on over the denominator, which is 3 plus 1, so it's going to be a quarter. So therefore from this we can figure out DC, because we know that it is 3/4 of BC, which we know as A. So therefore DC is just 3/4 of A. We can also figure out CF, DF, or FC more specifically, because what we can do, we know what AC is, it's B, and because we're told that F bisects AC, remember bisects means it puts it into two equal segments, then what that means is this is going to be a half and a half. So therefore FC is going to be half of B, and therefore we can figure out DF, because D of F is going to be equal to, so if we go along here, it's going to be DC, and I'll add the arrow here for where we're going across, plus CF. Now, we are now going at the opposite arrow to where we found the vector FC, so that means that this is going to be equal to DC minus FC, and all we just now is just to plug in the values. DC is equal to 3 over 4A, as we figured out up here, and FC is equal to half B, so therefore it's going to be minus half of B, and that is what DF is. So for part B, I have such little spaces, so I'm going to have to try and squeeze this in. The area of a triangle is equal to half times base times height. So the triangle is obviously this thing here, and this is the base. If you want to, you can flip it 90 degrees in your head in order to see that this is the base, and this is just going to be equal to the vertical component of B, because you can see it's the same size and parallel, so it's just going to be that, and this is 10. So therefore the base is just going to be equal to 10. Okay, now the height is going to be this part here. This is going to be the height. There's two ways of doing this. The first thing you could do is realise that this is going to be the horizontal component actually of DF, and therefore if you want to, from our previous equation, you can use DF in order to figure this out. The other way you could actually do it, though, a lot simpler, is this is A up here and this is parallel to A, and we know that, well, more specifically, this is parallel to DC and it's the same size, and we figured out DC from before. It's 3 over 4 of A, and now we know that 3 over 4 of A is going to be 3 over 4 of 12, 0, which is equal to 9, 0. And therefore the height is just going to be the horizontal component of this, which is 9. So therefore the area is equal to half times the base, which is 10, times the height, which is 9, and if you put that into a calculator, that is equal to 45, and that's the final answer.